We now welcome to the stage Adjunct Associate Professor Max Zanin, the Managing Director of MZ Minerals and a Chief Investigator in the PRIF Mining Consortium and the ARC Training Centre. Max is a mineral processing engineer with 20 years of experience in research. Through his dual role of Managing Director of MZ Minerals and Associate Professor at the Universities of South Australia and Adelaide, Max has developed high international recognition among both the global mining industry and academia as a flotation expert. Max takes the same passion for recovering value from what other people consider waste into his personal life. Max drives a 1979 Toyota Corolla, still has a fully functional 1979 CRT TV in his kitchen. I don't actually know what that is. And distills his own grappa. Of course, it's for personal use and within legal limits, apparently. Welcome, Associate Professor Max Zanin.
Well, thanks, Ruth, for the very nice introduction and also for disclosing my alcohol smuggling activities. By the way, I noticed that Brett Triffett was presenting remotely and he couldn't collect his bottle of wine, so I'm more than happy to collect his if he doesn't want to. Anyway, back to serious stuff. So, as Ruth said, my personal interest is flotation. Basically, I developed my career around flotation, both in the academia and as a consultant. So today I'm going to talk about flotation. And my involvement in the PRIF, of course, has been mainly in Program B, supervising the PhD students and giving advice in the translation projects, which are of real interest to me. I want to see things happening in the plant, and therefore the translation projects to me were the winning point for the PRIF. And I was very happy to be involved and see things happening with the help of Richmond, which was very useful in doing a lot of very interesting stuff. So, where do I start? I guess this slide is not taking anyone by surprise, so it's been discussed before, and we know that there is a decline in the availability of very nice ore bodies, so the good old days of 5% copper head grade are gone, and the future of the mining industry will be facing low-grade deposit, difficult to mine deposit, scarcity of water, cost of energy, and therefore there is a need for new technologies, more efficient technology, leaner technologies to be able to make projects viable. So last year in my presentation, I gave a 3D animation, a rendering of what the flotation plant of the future will look like. And in this flotation plant, there was a lot of implementation of new technologies. So you can imagine that some of the traditional bank of flotation cells are replaced by dedicated pieces of new flotation cells, like the Jameson cell or the Stack cell, Hydrofloat, or other things. At the same time, we saw in the flotation plant of the future a lot of sensing, and it's all the things that the PRIF has been working on. So we have the real-time sensing of pulp chemistry using the Magotteaux, inline particle size analysis, acoustics, vibration, and also measurement of collectors and frotter in solution, which will help dosing reagents properly. So a lot of things that are now just under development will be a standard in the flotation plant of the future. And not to mention machine learning, which we all know will play a major role, because we would like to achieve a plant which can learn by previous operation and adjust real time as the feed characteristics change. And this would be the big advantage and a big goal. Okay, this year I'm not going to talk about the different technologies as I did last year. I'm focused more on the application of these new flotation technologies and how I see and we see development and application of these technologies in the real world. And I have to mention that we recently started at UNISA with Bill Skinner, my colleague Bill Skinner, a specific project which is called Advanced Flotation Project, which has a very applied component. And we have a number of listed there partners, industry partners. The key point I want to say about this project, because the discussion went on earlier this morning about involvement of PhD students with industry and their research. In this project, the PhD topics have been discussed and defined closely with the industry sponsors. And our industry sponsors are being approached not at the corporate level, but at operational level. So we have individual champions within the different companies Two of them are here, Grant Small and Chris Creed from Magotteaux, but we also have other champions for each of the other sponsor companies. And sitting in front of them, we discuss what would you like to happen in the project for you? What would you like to see in your plant, on your ore? Can we discuss a PhD topic which is of interest to you? So the PhD students we have in the project are working on a specific project for a specific company on their ore. And they're supervised jointly by relevant people in the company. This is the way we think may provide a good outcome for both the university and the industry partners as well. So this project started this year, and it will last for 3 more years. So we basically just started. And it's focused on implementation and applying new flotation technologies on the sponsor ores and the sponsor plants. So we want to see things happening and how this can be tested and put on practice in the real world. One examples of the technologies we are implementing in the project, we have hydroflow flotation, which is emerging for the flotation of coarse particles. We have the reflux flotation cell, which is emerging technology for improved recovery grade in fine flotation feeds. And we also focus on dry comminution, dry grinding rolls, and also combination of dry grinding followed by hydrofloat. So we're open to thinking outside the box and developing processing route, which are a step forward compared to what is the current best practices in the plant. Specific project objectives of this, which we call advanced flotation project, is to target coarse and fine particles separately. As an example, this graph here it's very popular for people who are familiar with flotation. It's called the elephant curve, and it shows that typically flotation in mechanical flotation cells drops in efficiency as you move to the coarse end of the particle size distribution and to the very fine end of the particle size distribution. So what we are trying to do is to be more efficient in recovering the coarse particles and the fine particles. But I want to say something, don't misunderstand me, because in the last, let's say, 10 years, there have been many new flotation devices which have been developed and offered to the market. So there is a lot of new machines around it. And I have to say that I'm a big fan of mechanical flotation cells, because mechanical flotation cells are reliable, they're easy to operate, they're relatively inexpensive, and they are arranged in banks. So if anything goes wrong in one cell, you can still hope that the following cell will recover that stuff. So in principle, they are a robust technology. But if we really want a step forward in specific applications, so not everywhere, but we want to target very coarse particles to save energy for grinding, or we have an issue with fine particles because slow flotation rate, then we need to look at modern and different technologies, and this is what we would like to test in the project on specific company ores. All right, I'm not going to explain the technology because that's not the aim of my presentation today, but fluidized bed flotation is specifically designed for coarse composite particles because they can easily get to the concentrate without detaching from bubbles. And we want to see how in practice this can apply to different ores. Can we extend the particle size range? What's the benefit for individual sponsor companies? And the same thing applies to the reflux flotation cell for fine particles flotation. But what I wanted to talk today, since I only have 15 minutes, and probably Ruth soon will tell me to stop, is the application. Because we know that it's been said before that environmental sustainability is now a well-accepted concept that everyone will have to follow, especially in mining. And actually there is a specific industry body, the International Council for Mining and Metals, which has been established just to look into sustainability in mining and develop guidelines and principles. And one of these principles that captured my attention is develop innovative approaches, technologies, to minimize and ultimately eliminate at all the production of tailings, of waste. So internal reuse, recycling, more efficient processing so that you can reduce to the very minimum the amount of tailings material. But the only way to achieve a zero waste policy is to improve your technology, so have more efficient flotation technology. So we need to work towards more efficient technologies to get to a zero waste situation. And within this scenario, one big area which will be of interest for many, many years now, there's an opportunity to recover value from all tailings, which has been disposed there for a long time, because back then it was considered to be waste material. Most of the time you have to treat that material anyway for environmental reclamation, for other reasons. So there is an opportunity to recover value from all tailings, which is what I'm very interested. As Ruth said, I like all things in operation. I like to recover value from scrap. So if you think about it, there are advantages and challenges, disadvantages in processing tailings. Some advantages is that tailings material, most of the time, are easily accessible. So you don't have to mine them from underground. They're just there in a tailing dam. You just shovel them out or something like that. So the cost for mining that material is minimum compared to primary ore bodies. Tailing material is already ground. If it is flotation tailings, it doesn't need to go through grinding again and spend a lot of energy for comminution. And of course, there is also an environmental benefit in reclamation of tailings. So you can imagine it's not just an enterprise to generate profit, but there is also some environmental benefit, and there can be some government assistance in doing that. What are the challenges? And the challenge is my area, is where I'm very keen on. This material is more difficult to float compared to a primary ore. In particular because most of the time tailings have been exposed to the environment for a very long time, so the surfaces of particles can be oxidized, they can be contaminated, there can be any sort of thing that complicates flotation recovery. And also generally they are very fine because they're being already milled to that, and they are very, very fine material, and fine material is more of a challenge for flotation. If you have particles finer than 5, 6 microns, as sometimes you have in tailings, they are more difficult to float. And of course, the first comment is, well, that stuff didn't float in the first instance, why should it float now? But we hope that now we have better technologies, and we know how to address things that maybe 20, 30, 40, 50 years ago, they were not able to address, and that's why that material ended up into the tailings dam. And the final thing is, normally it's very low-grade material, but as I said, not always, because the low efficiency in the past made material which was a relative high grade ended up into the tailings. So sometimes you have very nice discoveries. What I thought it was a tailing deposit, it's 2% grade zinc, 3%, so that's a good deposit to me. So there is pros and cons. And now I just give you a couple of examples of situation where a process for recovering value from tailings is actually happening, or is about to happen, or was about to happen, because it's a couple of projects I've been involved in one of them many times along my career, so I have a bit of knowledge about those systems. One is very well known here in Australia, and it is New Century. New Century, it's in northern Queensland. It's a zinc operation, and it is now reprocessing the zinc tailings from Century, which was the company who was running the mine when it was a primary zinc deposit. And New Century is an example of an effective way. So it is working, and it is producing a marketable and sellable concentrate, zinc concentrate. So you can imagine in the tailings dam at now New Century, there is about 77 million tons of zinc tailings at about 3% grade of recovered zinc. So it's a good deposit, actually. What can I say? In terms of mining, one of the strategies to reduce mining cost, of course, at New Century they use hydro mining. I don't know if you are familiar with that, but it's quite interesting to see. It's just a strong water jet which is breaking down aggregates and basically repulping the stuff, which then goes to the flotation plant. So you don't have the cost for mining, you have little cost for comminution and grinding. That's why the operation is cost effective by doing that. And I quite have a long history with Century because we were involved in a couple of projects back with Amira, and it was a UNSA project which was called the Froth project to optimize froth stability, when still it was Century mine. And there is a unique thing about that ore which was detrimental for flotation, and it was the presence of organic carbon, what it's called pyrobitumen. It was organic carbon in the sphalerite ore, and that organic carbon in the flotation feed was behaving like activated carbon. So it was absorbing all reagents in the system. And it was quite painful for operations because we did just a mass balance of the amount of frother, surfactant that they were adding, MIBC. They had to add about 400 grams per ton of MIBC. And out of those 400 grams per ton, just about 15% was still in solution after addition because all the rest was absorbed by the carbon minerals. So there was a huge problem of consumption of reagent. And they addressed the problem by introducing a pre-flotation stage to remove carbon as early as possible to prevent that stuff for causing further damage down the bank. Today, the situation is improved. Carbon in the system is more under control, more or less under control, so it's not the same as in the primary ore, but still at New Century there is a focus on reducing reagent consumption and optimizing froth stability, ensure that the plant runs stable from a water chemistry point of view. And this is why I was thinking about what we've been doing in the PRIF and things which are outcomes of the research done in the PRIF, which could be beneficial, in particular for water quality control. So being able to have a real-time concentration of some molecules in the system, and I'm thinking about the gravimetric methodology for frother or collector, which was developed in the PRIF. Being able to measure critical ions in solution with the MOFs or optic fibers and those things would definitely be beneficial to have a real-time control of water quality, because water quality is very relevant for operations at New Century now. So I'm just thinking forward of some of the possible outcomes and benefits of what we've been doing in this project. And the other one is in a completely different part of the world. It is in Brazil, Três Marias, Minas Gerais. And it now belongs to Nexa Resources. It used to be Votorantim when we did some work for them. And this is a situation which is not unusual in several parts of the world. So there is a huge tailings dam which contains residues from a zinc smelter, which has been operating a variety of different ores, sulfide ore, silicate, zinc ore, by different processing routes. So some acid leaching, roasting and leaching, flotation, and all those tailings have been accumulated in this big tailings dam, which, guess what, is standing just nearby a very important major waterway, a river. So you can only imagine the environmental damage if anything fails in that situation. So there is a lot of pressure in reclamation of that area for safety and environmental concerns. So the project is, can we do that and make it viable from an economic point of view? Because that stuff contains decent amount of zinc and silver. So can we float that material and make it viable? And so the company started looking into this about 10 years ago, and several different research centers and universities work on this. And we got a project at UNSA about 5 years ago as well. And so we tried to develop a flotation strategy for this material. And I decided to include this in my presentation today because this is the perfect example of a metallurgist's nightmare. Material from that tailing dam didn't look anything like a real ore. Basically consisted in agglomerates of very fine particles of sphalerite and other minerals in a kind of amorphous matrix of gypsum and calcium, magnesium, aluminum silicate, zinc silicate stuff. Kind of something that you don't know how to deal with it. Because ideally the only floatable species is sphalerite, which is the zinc sulfide, and the silver sulfide, silver in the sphalerite. And those were just very finely disseminated in this sort of amorphous matrix, which was almost impossible to recover. So the strategy here was to start with attrition, to disperse as much as possible particles, desliming to remove as much as possible of the fine gang, and then flotation with a lot of optimization of the reagent scheme, because that material has been exposed to the environment for 40 to 50 years. So you can only imagine surfaces, how did they look? We had to make them hydrophobic again. And back then, it was half of a failure because we managed to get target grades for the concentrate. We were able to produce a 40% zinc concentrate and 3,000 ppm of silver, so it was not bad. But still, recovery was insufficient, was not high enough. because those particles are very, very fine and very low flotation rate. And this is my observation now after many years of PRIF. Back then, we did optimization of flotation just using traditional mechanical flotation equipment. What if we use more advanced technologies? So could we do better today? And this is why we think of projects like the Advanced Flotation Project, where we put technology to practice. This would be a perfect example to test the new technologies. So what if we use the reflux flotation cell? Can we get better grade because we reject the gangue much better? Can we do Jameson cell, high energy, high shear? We can increase the flotation rate of fines. So can a project which was not viable 5 years ago become viable now because of implementation of new technology? And I guess this is the goal that all research projects should have. And I'm very pleased of having been part of the PRIF, because that was the aim. Let's develop something that through the translation project can go to site and can provide a benefit and make some operation which is now not viable economic again. Brett Triffett this morning was mentioning that in South Australia there is a number of sub-economic deposits right now. Maybe with new technologies, with sensing, with machine learning, we can shift that line and make them economic. The same applies to recovering tailings from operations. We can become more efficient and make the thing economic as well as an environmental benefit. So the key comment is that the ultimate goal is to turn non-viable projects into viable projects. And I just close my talk with this slide, just to remind everyone. Some people say, why bother about tailings? Well, sometimes thinking about tailings when it is too late is much more expensive than thinking about tailings when you're still in time to do something. And so this is just one of many, many examples of things that can happen when tailings facilities go wrong. So why not looking into those for the environment and trying to get some value at the same time, which is my interest and my passion right now. Thank you.
Do we have any questions for Max? Everett's just coming behind you with a microphone.
Thank you, Max. This is very much a layperson's question. I'm just wondering, when you do additional metal extraction from tailings, you still obviously have a waste stream at the end of that. Is there any beneficiation that occurs to that waste stream, taking more metal out of it, and those fine particles, that silt material that's left over, has that got any applications in any industries anywhere?
Well, yes, I can tell you something for the little experience in the area I have. But of course, the whole idea is try to recover value as much as possible, but then at the same time, maybe to find a better use for that material. So there is some secondary products that you can use rather than stocking that stuff in a tailings dam. If you can reduce the content of metals, for example, below a threshold, you can reuse that as backfilling material or to brick construction if it is suitable. So the idea of reprocessing, from my point of view, is metallurgy, so get value. But then I know that there are a lot of possible applications for those materials rather than disposing them again. So it should be a comprehensive operation which involves both recovering value and trying to find a better destination for that material rather than disposing it again.
Supplies sand for the building industry and what have you. But Europe doesn't mine sand anymore, it's illegal. Nobody's started to hack into the Sahara Desert yet, but it is becoming a growing problem.
Yeah, Chris, the only things for using it as sand is to reduce the amount of penalty elements to below a threshold limit. Yeah.
Professor Bill Skinner is the PRIF Mining Consortium's Program B leader. Bill has over 30 years' experience in R&D. in understanding the physics and chemistry of minerals in processing. In addition to Program B leader in PRIF, Bill is a research professor in the minerals processing at the Future Industry Institute at the University of South Australia, Deputy Director of the ARC Centre of Excellence for Enabling Eco-Beneficiation of Minerals, and Deputy Director of the ARC Training Centre for Integrated Operations for Complex Resources. Bill's research focus is enhancing productivity while reducing energy and water and the overall footprint, which is a key objective of PRIF. Outside of work, Bill loves people, food, wine, gin, cooking, growing chilies, and trying to play the guitar. Welcome, Professor Bill Skinner.
Well, thank you, Ruth, for that introduction. I share their love of old things too with Max. I used to have a 1979 Corolla station wagon. I had it for 30 years, but unfortunately it died by origami. It got folded up and dumped after 35 years. And I also have a 1967 Echo Barracuda. Now, only Grant Small will know what that is. It's right here. That's a guitar, electric guitar, Italian electric guitar. They were brought out by Vox in the early 70s. Okay, so I'm going to talk about a little bit about Program B and introduce what we've been doing. So, this thing, okay, technology, isn't it wonderful? So, Peter showed this diagram, and this is to show you the circled region where Program B sits. It overlaps with Program A in that the kind of material entering to the mills is very important in determining the products of those mills in terms of particle size, but also chemistry. And the projects in Program B cover things around the mill, including particle sizing and cyclones, looking at flotation in terms of sensors, and also modelling the performance from bringing chemistry into the parameters that you measure at plant. And Richmond later on will be talking a lot about that, the work of Bismarck, etc. And then at the leaching end, projects that revolve around sensing of reagents and or ions in solution, as Max was mentioning earlier. Very, very important. And most plants in our history, particularly history of me and Max going way back, you go to a site and they say, well, yeah, we measure chemistry, we've had pH probes all over the place, and you go and have a look and they're all broken and whatever, but they were wonderful pH meters, pH probes, because they registered pH 9.5, exactly, all of them. So we're all fine, you know. Process is so fantastic. All right, so Peter showed a nice sort of circular, if you like, the machine learning side of the supply chain, or sensing and data analytics in the supply chain. So what we're looking at here downstream is feeding information back upstream and getting it incorporated and being available to upstream in order to determine what was the material that we be able to tag a piece of material that came to the plant and then performed in this way. And by doing that, you're able to go back up each unit operation and say, well, okay, this is what we were doing wrong at this point. Let's adjust. And the whole exercise, pretty much the whole of the PRIF and of the training centre, is to take variability and minimise it. If you minimise variability at any point along the chain, you're able to see improvements and decrease in performance much more readily, because you're now outside the noise. But it also gives confidence for that plant for its production as well. So in the themes here, we maximise mill throughput, constraint mineral liberation, but also following on from that into the training centre, looking at mill health, etc. Maximising the copper recovery, looking at the modelling of the performance, both from existing plant data and by introducing chemistry variables into that, mainly through the Magotteaux pulp with Chris Greet's wonderful device, that one which is sitting up at the Olympic Dam at the moment. Don't smile, Richmond. So integrating the grinding sensors and data with the flotation data, that gives you another lever to be able to pull and highlight variability, but also optimise. And lastly, look at ions in solution throughout the plant, not just in leaching, that are critical for that process, or process efficiency. So Program B has its list of translation projects and linked research projects. We'll go into a couple of those in the next slides. And the key industry partners in terms of technology partners are Magotteaux and Manta Controls in this regard. So, the research projects. We've got the sensing and optimisation of ag and sag grinding mills. This is all around a vibration measurement of mills. And in that, Kwaku Boateng Owusu, he is now graduated, and he has a, I think it's called a CSIRO Early Research Career Fellowship, and he's gone back to his love of pyrometallurgy and steel making. So he's in Melbourne now, so he's finished up, and in that he worked with Magotteaux and built a laboratory scale sag mill for doing vibration measurements in the lab, and to look at the changes in those vibration that you achieved when you changed feed ore types, mainly around hardness and proportions of hardness of different minerals in the system, and was able to show you could, in the frequency domain, detect changes in hardness. Again, around the mills, we've had a stream of honours and MSc students working with Lei Chen. Is Lei here? Is Lei here? No. Can't see him. Lei Chen, and there's still some work going on this with these three new master's students, or is it four? 1, 2, 3, 4, 3 master's students who are continuing on with some of that work. The highlights, the yellow highlights here are indicating projects that actually are going on either in the PRIF extension, in the training centre, or in some other mode associated with the PRIF or training centre. Difan, whom you'll hear from later today, my God, I'll buy anything off this man. He'd be really good on the Shark Tank. He always starts his talks, I'm not going to preempt, with a statement that really sucks you in. I think it's great. So he's been looking at, what was that? I thought someone said something. He's been working with a sensor for measuring particle size in hydrocyclones. And through some of that work, he's even been setting up equipment at UniSA and our labs because we can handle BHP ores, which have low-level radioactive content. Bismarck Amankwa, Kirama, he's completed his PhD, and he was working on the modelling of flotation performance using data from the plant, but also the chemistry, and it's quite interesting, the work there showing, well, you model the performance without chemistry, and you put the chemistry in, and suddenly everything sharpens up quite nicely. Bismarck was pretty well much whisked off to Western Australia to go work for Talison Lithium. I think even before was that even before his graduation or was after? Just before his graduation. We've heard about some of the, I mean, Nigel mentioned at the micron scale or even below the micron scale in terms of sensors. And this is looking at a very new approach to sensing particular metal ions, particularly ferrous and ferric ions by difference in flotation pulps. Linda Rosenberger, who is 99.95% finished. We're waiting on the examiner's reports, but Linda is now working with Zeiss here in Adelaide, and that project was ably backed up by some of the mathematical modelling work done by I think we can call her Doctor now. I think she had the letter that says she can use the title Doctor, but it hasn't been to graduation yet. Supervised by Bronwyn Hayek, who is up the back there waving. And Kirsten looked at modelling how these metal ions in solution react with these metal organic frameworks in real solution. So the idea behind this is you get metals absorbing to or in, it turns out to be to, these MOFs, which then change their spectroscopic characteristics, and you see a characteristic loss in peaks in the infrared when you have iron 2 absorbing to that. So it's a really interesting way of indirectly measuring the iron 2 concentration, and you whack it on an optical sensor. So those two projects, 5 and 6, work pretty closely together, and it's a real example of how the mathematical and the experimental can work really nicely together. Kirsten's in Queensland at the moment, but is going to be doing some work with Richmond in the near future remotely. And the last one was we had extra involvement of Dr. Todd Gillam, who is working with Anton Blenko. Anton's up the back there. If you haven't met Anton over the years, you need to go and talk to him. He loves growing chilies too. And now Todd is still at UniSA, but he has a DSTG funded fellowship to work there. And Todd was working on the gravimetric centre for flotation frothers, which Max mentioned. In the translation projects, we had the Manta mic acoustic devices set on the ag mill, and that was again with Kwaku in Richmond, and that was completed. We only got short distance using these ultrasonic PSD particle size distribution sensors for the grinding circuit, only because when we got to that stage, this was going to require a large-scale investment from BHP at Olympic Dam in order to get that equipment into site. And it's still ongoing discussion, but it all has to be around the business case and the value proposition for that equipment to be in place. Pulp chemistry monitor, I've mentioned this, which is with Bismarck and Richmond, and that's being selected for extending within the PRIF extension over the next year and a bit to try and push that further along the commercialisation pathway. Linda's work with the MOF sensor is being taken over now by Piotr Pawliszak. Piotr, hand up over there, with a beard that's really magnificent, much better than mine. Wait till you get grey in it, mate. So that work is going to continue, but they're targeting other funding sources for that in collaboration with Magotteaux, whether it be a CRCP or a seed grant or something like that, because that requires a couple more years of work in there, since there's about 3 different bits of technology that have to be developed together. And the last one was the building the lab-scale ag-sag mill, which I mentioned earlier had been completed actually quite early on, otherwise Kwaku wouldn't have been able to do his work. So I want to show people, the ones with stars on them are people who are still going to talk or have spoken already. I must give a particular shout out to Richmond and Difan, who've been the postdocs on the project from the beginning, and especially to Richmond at UniSA. I've got to say, backbone, mate. You held everything together as far as the translation projects were concerned, and with the supervision of particularly Bismarck and Kwaku. So we've got Kirsten, we've got Kwaku, we have Bismarck with his new best friend, who he finally got to graduation, got to meet a koala the first time. Piotr, who's just joined us, Todd, Linda, Jeff Boobin, Dale Otten, and of course David Lancaster, who had to step back from the PRIF because he had to take up a new EOS chair in laser physics. The TRLs, won't bore you with these, but just to indicate that the things with a star and an arrow, they're the things that are going forward in the extension to the PRIF over the next year and a bit. So we've got the measurement of particle size and hydrocyclones, and we've got the pulp chemistry monitor-based things, and the modelling of flotation performance using both plant and new additional data from chemistry. Acknowledge all the supervisors and our contacts at BHP and our translation partners, particularly Chris Greet, whose adjunct status at UniSA came through early this year, and John Karageorgis from Manta Controls, and all our sponsors. And lastly, congratulations and well done to all. I know we've got this up on things everywhere, but that was a really great night, and it's a wonderful thing to have someone outside the project, whether it be researchers or companies, look at what we've been doing and saying, hey, this is valuable. And receiving this commendation was a pretty nice cherry at the time. I think you'd agree, Nigel and Peter. So I'll leave it there, and thank you very much.
Any questions for Bill? No? Excellent. Let's move on.
I didn't touch it.
It's all right. I'll take it. We now have our second joint research presentation from Dr. Difan Tang, a postdoctoral research fellow from the School of Electrical and Mechanical Engineering in the PRIF Mining Consortium, and Lin Yang, a PhD student from the School of Electrical and Mechanical Engineering in the ARC Training Centre, both at the University of Adelaide. Difan was a mechanical engineer at a CAD software company and joined the PRIF Mining Consortium as a postdoctoral researcher in 2019, undertaking the hydrocyclone project with research interests in advanced and affordable online particle size sensing. Difan enjoys driving manual cars, and he hopes his next car will be an electric one. And if he can't find an electric manual car, he vows to make his own. Lin Yang's PhD research focuses on early roping detection and performance monitoring of the hydrocyclone. His research interests lie in the fields of intelligent sensing and mechatronics engineering, and he is committed to applying sensing systems to the mining industry. When he is not in the lab, you can find Lin on the tennis court. Welcome, Dr. Difan Tang and Lin Yang.
Thank you, Ruth. Good afternoon, everyone. Driving a manual car, for me, is just for fun. But I believe automation will be the future. This is the same in the mining industry. In our project, we developed a new sensor for hydrocyclones in the comminution circuit to help enable automation of the comminution. Then why do we need automation, and why do we need the sensor? This is because almost 50% of the total risks in the mining industry come from energy-related matters. And comminution is a giant in energy consumption. I think most of you may agree that it's very difficult to reduce energy consumption for a particular given mineral processing plant. Then what else can we do? We can do automation. Traditionally, particle size analysis is done offline, which can lead to hours of delay and result in large variability in the products. Now our sensor comes in here. It monitors particle size online in real time and feed the information back to an automatic controller that will adjust the operation parameters accordingly. And that helps reduce the variability, helps increase the throughput, and helps improve the flotation efficiency. And most importantly, at the same energy consumption level. So here is our sensor. It comes with an interchangeable probe inserted into the overflow pipe, and with the main measurement unit, a force transducer, mounted outside the overflow pipe. We also have a couple of accelerometers installed just for lab purpose. It may not be included in the final product to reduce the cost. This is a multifunctional sensing system that will deliver not only the size passing fraction, but also the mass flow rate and also flow viscosity. I will cover that in more details shortly. We have been trying to minimize the cost of our sensor to maximize the benefits it can deliver. Here is an example of the benefits. Let's be conservative and assume just 1% of throughput increase. And that we will be expecting an additional revenue of around $30 million. If every hydrocyclone unit is monitored by the sensor, then we can largely prevent bad operations that result in hydrocyclone faults. Assume 1% of recovery loss can be prevented. Then we will be expecting an additional revenue of around $3.5 million. And how about the cost of the sensor? You'll be looking at just a tiny bit, and the benefit is obvious. To lower the cost of the sensor, we have developed a unique way based on force measurement. The probe is subject to vibration under particles impact and also flow-induced drag. Depends on the vibration frequency range. We apply two different models, mathematical models, to extract useful information from the signals. That includes the mass flow rate and also the flow viscosity. That's why this is a multifunctional sensing system. With all the available information fused together, we will be able to obtain the particle size distribution. To understand the probe response under particle impact, we started with testing in dry conditions. And that is shown useful in applications beyond hydrocyclones. I will cover that in more details shortly. After the dry test, we move on to more complicated scenarios involving slurry in a small-scale closed-loop flow system. And to test the scalability of the sensing system, we have also done some tests on a larger scale over closed-loop flow system. So this is the main results. We use laser measurement as the benchmark for comparison. The sensing system starts with an initial approximation of the particle size distribution and finally converge to an optimal approximation that is very close to the laser measurement. This is updated in real time and sent back. It can be sent back to the automatic controller to enable automation in grinding and hydrocyclone operation. Apart from the particle size distribution approximation, the sensor can also be used to detect hydrocyclone roping. Lin Yang from ARC Training Center will give you more details about this. But before that, let's have a look at something different. in dry conditions beyond hydrocyclone. Nimble Resources has their unique dry production for alluvial gold mining using their rotary air concentration. They are looking for something that could monitor the density of particles in the concentrates. So why density but not size? This is because the concentrates and tails have large portions of particles within the same particle size range. So looking at the particle size does not help. Instead, if we look at the density distribution against particle size, then the concentrates and tails are very different. So now the question is, can our sensor monitor density? This is our experiment. The hopper is first loaded with concentrates, followed by tails on top. And our sensor is placed underneath the hopper to receive the impact from particles in free fall from the hopper. Initially, there is a transient period of 2 seconds, but after 2 seconds, when the concentrate mass flow rate stabilizes, our sensor records a value that is the density of the concentrates. And shortly after, when the tails start to mix with the concentrates, we can see a gradual change of the measured density. And the measured density starts to stabilize at a low level when the remaining particles are all tails. So this shows our sensor can be used to monitor the density change for the application of Nimble Resources Gold project. You might be wondering, could particle size distribution be also available in other dry tests, in other dry applications? The answer is yes, and Lin will give you more details about that.
Hi everyone, I'm Lin Yang from TC Training Center. So thanks for Difan for the detailed introduction. And as Difan mentioned before, our sensing system can measure in the particle size distribution and the mass flow rate of a dry high intensity particle laden flow. So here are the test sample that we have for the dry test, which is 4 groups of quartz particle with the different but also similar size range and particle size distribution. The left-hand side figure shows the particle size distribution, which is measured by a Marvin Master Sizer 2000, which is an offline laser-based method. So we use this result as the benchmark of our test. And the percentage passing size is also shown on the right-hand side figure. So on the left-hand side, which shows the relationship between the sensed average force and the mass flow rate. As can be seen from the figure, there is a high agreement between the average force and the mass flow rate. There is a linear relationship, and the red dashed line, which is the predictive model that we developed based on the impact mechanics. And the right-hand side figure shows the shows the modeled particle size distribution based on our model and the sensing signal. The red dots is the benchmark measured by the Master Sizer 2000. And the red curve is one that we modeled with a pre-assumed log normal distribution. And the roping detection is also important, as is mentioned by Difan. So right-hand side figure shows the roping in hydrocyclone. When the roping happens, the underflow mass flow rate will reduce, and the coarse particle will go from the overflow instead of the underflow, which will reduce the separation efficiency and then affect the flotation process and the final productivity. So, so on the left-hand side, it shows the transition from the spray to roping of a hydrocyclone working status. One difference is that if we look at the underflow discharge angle, when the roping happens, the angle decreases. And the other difference is that the overflow air core will disappear when the roping happens. So based on this, we got our method to detect the roping by using our force transducer. So by mounting the force transducer at the overflow of the hydrocyclone, when there is a spray working conditions, which is the normal working conditions, the overflow will have three-phase flow, which is the gas, liquid, solid. But when the roping happens, the air starts to decrease, the air volume, and then the three-phase flow will become two-phase flow, which is only liquid and solid. And it will cause the change of the effective viscosity and the resulting the change of the drag force. By combining the change of the drag force and the particle size distribution, then we can detect the roping. Here's the results by using the sample from a mine site. Thanks for Max for providing the samples. And as can be seen from the left-hand side figure, there is a difference with the involvement of the air of the pipeline. And there is a distinguishable difference that we can tell with and without air. And the right-hand side shows the difference in different flow rates of the slurry. It is exciting that the current development of our sensor, all of these functions, but our sensor can be used in more and more industries. I will let Difan to conclude.
Thank you, Lin. Beyond application in hydrocyclone and beyond the mining applications, our sensing system can also be used in fields like power plants and also powder manufacturing, as long as it's something dealing with particle size monitoring, no matter whether it is dry or wet. And we are looking to install our sensor at hydrocyclones at one of the listed mine sites. And we are also planning to try the sensing system on the vertical roller mill at BV, and also try that on the rotary air concentrator at Nimble Resources. On behalf of Lin, I would like to acknowledge the great support from the ARC Training Center and all the industry partners involved. And I would also like to acknowledge the great support from the PRIF Mining Consortium, my supervisor, our end user partners, our translation partners, and also Lin. That's all of our presentation. Thank you very much for your attention.
Any questions? Everett?
So, I mean, that's a great talk. I mean, you really sold us. It's fantastic. You just get better and better presenting. How would you envisage the potential market for this technology?
The market for mining industry, the potential market is huge in the mining industry, as you can see from the case study at BHP Olympic Dam. And apart from that, it is also potentially applicable in other fields like mentioned in the slides, in power generation, in powder manufacturing.
Cocaine, I was thinking, when I looked at those images there. You were talking about cement and cereals and baby powder and stuff like that. That's fantastic. Thank you.
Thank you.
Thank you. Dr. Dylan Peukert is a postdoctoral research fellow from the School of Chemical Engineering in the ARC Training Centre at the University of Adelaide. Dylan has a physics background with expertise on the use of radiation and nuclear modelling to solve interdisciplinary problems across industry and medicine. Currently, Dylan is researching the use of computational modelling to help improve and extend the application of prompt gamma neutron activation analysis sensing for ore sorting. Other sensor models are also being developed to aid the evaluation of sensor fusion for ore sorting. Dylan didn't provide any tidbits, but I do know that he is an encyclopedia of knowledge with regards to Indian food, and he bakes a fantastic Christmas stollen. Welcome, Dr. Dylan Peukert.
So welcome. Today I want to talk about my research, looking at sensor simulation for improving ore sorting. So my project at the training centre is looking at optimizing sensor-based ore sorting, diverting waste before it's sent to the mill. Combined with all of the other projects at the training centre, is designed to cooperate together and solve problems to improve processing for complex resources throughout the entire mining and processing chain. So the key points that I want to get across today is that sensor simulation can help implement and improve sensor-based sorting. It can help evaluate applications of sensor-based sorting, as simulations can model the response for a wide range of materials and sensor conditions, enabling an initial evaluation for given applications. It can also be used to help optimize by separating signal from background and interrogating the effect on both of these under different conditions, helping analysis. So why do we want ore sorting? The main issue is that global mineral demand is projected to rise dramatically from the energy transition and a growing population. Meeting this demand with traditional methods which require great cost, great resource consumption, and produce large amounts of fine tailings. So we need to find better ways to do this. One such is the use of sensor-based sorting. By removing waste material before extensive processing, reduces the cost, reduces the resource consumption, and reduces the production of fine tailings waste. A key sensing technique is the use of prompt gamma neutron activation analysis, or PGNA. These sensors can provide the multi-elemental composition of the processed material for large quantities of bulk material, making it ideal for bulk sorting for high output mines. And my research is looking at developing a sensor model to help improve and extend the application of PGNA sorting. So I've been working closely with partner organisation Scantech to develop a model of their GeoScan PGNA sensor within the GN4 Monte Carlo toolkit. One of these sensors is pictured here, and this model has been validated with experimental measurements. So today I want to present the use of this model to investigate a range of characteristics, including the sampling distribution, the effective material thickness, and moderation, as well as the investigating model to help improve analysis, such as by building elemental libraries and isolating the signal. So taking a look at the first of these characteristics, the simulation can record the origin point for every recorded photon, which can enable the sampling distribution for the tested material to be determined. Here we can extract the 3D distribution, and we show 2D profiles from the front, side, and above. It is possible to see that the sampling is stronger towards the center and towards the base, which is closer to the isotropic neutron source. However, a high level of sampling is achieved throughout the entirety of the material, in this case a 5 centimeter thick iron ore copper gold model, which enables the reduction of biases, which is problematic for other sensing techniques which only sample a single point or a surface. So we can also use the simulation to investigate the effect of sample thickness. As while the same elemental balance is present, the level of thickness can affect the response. Here we can see the energy spectrum of the recorded photons, with characteristic peaks corresponding to both the sample and the components of the sensor. And we can see that for different sample thicknesses for the iron ore copper gold material, we can see that there are complex differences in the spectrum. The simulation can be used to help interrogate this and understand what is going on, as it's possible to separate just the signal from the background noise. Looking at the signal on the left, it's possible to see that with increasing sample thickness, the signal begins to increase up to 10 centimeters, after which there is a decrease. This increase is due to there being more material to be sampled, but also due to the reduction of the neutron energies by moderation, boosting the activation potential. But we can see at greater thicknesses, absorption of the signal photons does reduce the measured signal. However, if we look at the noise, we can see that there is a clear and consistent reduction of noise with increasing thickness, due to both neutrons and photons being absorbed within the sample, reducing that noise and help boosting the signal-to-noise ratio. There we go. So, we mentioned the impact of neutron moderation, which is beneficial for measuring larger samples. However, if you want to measure a small amount of material, it's possible to use the moderating material to reduce this neutron energies and get a boost in the sample activation. To test this, a consistent 15 kilogram titanium oxide or root-out sample was measured, both alone, with a moderating polyethylene plate below, and sandwiched between two moderator plates, as shown on the right. The resulting signal is shown on the left, and we can see that the main titanium peaks located between 6 and 7 MeV are significantly increased with the addition of the moderation, showing that even if the same amount of material is possible by good design to help boost the measured response. This can be further illustrated by separating the signal from the background. As we can see on the signal on the left, a consistent increase across the entire spectrum, as the additional moderation boosts low-energy neutron flux reaching the sample and boosts the measured signal by increasing activation. There is another benefit that the absorption of neutrons within the moderator reduces the background, as shown on the right, where there's a consistent reduction, apart from the hydrogen peak at around 2 MeV and the carbon peak near 5 MeV, due to the presence within the moderating materials. So, as well as being able to test a wide range of characteristics, the simulation can also be used to help build elemental library spectra to help the analysis. So, to investigate this, a wide range of 30 kilogram sample responses for a range of elements was modeled, and we can see that there are a range of total signal photons shown on the left, as well as different effects on the number of background photons as shown on the right. So you can see there is a wide range of response, and we can see, interestingly, the background noise is more reduced for materials that are good at effective absorbing neutrons, such as hydrogen and boron. So as well as the total number of photons, we can extract the relative energy spectra. As shown on the left, we can compare the signal from 30 kilograms of sulfur and 30 kilograms of iron. We can see there are differences both in the total strength of the spectrum, as well as the position and strength of the energy peaks, which is what is used to determine the relative composition of the material from the spectrum. Looking at the background, we can also see that there are complex effects of the material on the background, as the varying neutron and photon absorptions of the sample can have a complex behavior on the background. So why do we want these elemental library spectra? It's because they can help us evaluate the compound material. So here we've scaled by the relative weight composition the elemental library spectra for the iron ore copper gold ore, and we compare it to the previous compound material thickness measurements. We can see for the 5 centimeter case on the left, there is a good match in the overall spectrum, meaning there is a good prediction. However, we can begin to see some variation between the library prediction and the compound material measurement for 15 centimeter. This is due to the fact that the relatively small samples are used, so for a thicker test case, there's differing levels of neutron absorption, which begins to result in differences between the elemental library spectra and the actual measured spectrum. And accounting for this could help improve the analysis. So I've talked a bit about how it can both be used to investigate characteristics and analysis. So what are the next steps? So I want to continually upgrade the simulation to improve the accuracy and better match the geoscan sensor. I'm also going to continue investigating signal analysis by helping to investigate the sample's effect on the activation spectra and investigate extracting the signal from experimental spectra. I'm also very interested in using the simulation to test a particular case study for a real ore and belt sample to see how it would, if the simulation can be used to predict the response of the sensor for a real mine. I'd like to thank the partners of the Training Centre and thank you very much.
Any questions for Dylan? Kathy?
Thanks, Dylan. Just a question. I'm not familiar enough with what was happening in Stream A. Did Scantech run their sensor up at Prominent Hill on the belts? Can somebody pick on that? Do you know?
I'm not sure if it's in so. We've got a couple people from Scantech here who might have some knowledge of.
No? Did you actually run a belt sensor up at Prominent Hill or Cara as part of this project? We're all one big happy family now.
So I've calibrated using test samples measured at Scantech's site. So I haven't.
Yeah.
So I'm hoping to. I know that there are Scantech sensors at various PHP mines, so I could test the simulation's ability to reproduce the sensor response.
It's probably very important at an IOCG because of things like the rare earths in there, low-level rare earths, particularly like cerium, and then with uranium in there, even though it shouldn't be a problem, but I would worry about the rare earths, even at very low, from other sensor trials, not with Scantech. So, so it's a question. You know, if you have some live data, that's better. You know?
So yes, I've modeled several samples. So ultimately, I'm interested in testing real-world ore samples. So, I mean, obviously there need to be some agreements in place, but the simulation could handle any elemental composition, no matter how complex, and compare the results.
Thank you, Dylan.
Thank you.
Our next guest speaker is Dr. Chris Greet, Manager of Mineral Processing Research at Magotteaux. Chris is leading Magotteaux's technical efforts investigating the effect of grinding chemistry on downstream processes. Chris has a real mixture of operational and research activities. He graduated from the South Australian Institute of Technology with a metallurgical engineering degree in 1990 and was awarded his PhD from the Ian Walk Research Institute of the University of South Australia in 2002. Chris has worked within the mining industry in a variety of roles, from shift foreman at the Teutonic Bore copper zinc operation to principal technologist with Pasminco. Chris is a leader in the mineral processing industry, leading the company's technical research, emphasising the close relationship between flotation and grinding, not only in terms of particle size and recovery, but also in terms of pulp chemistry. Welcome, Dr. Chris Greet.
Thank you, Ruth. you didn't dig up any dirt, which is good. Yeah, did you hear the one about the mineral, the reagent and the bubble? There is no joke. This is serious stuff. Basically, I'm going to try and talk about sensing and how you can actually use it in a concentrator. Then once you've done the sensing, you can then start using AI, machine learning and all that sort of stuff. Because at the moment, I don't think AI will work in a concentrator because we're not actually measuring the parameters that are actually critically needed to be able to apply AI. So there's the mineral, there's a reagent, that's potassium amyl xanthate and a couple of bubbles. So the idea in mining or in mineral processing is to grind the rock, put some collector on it, and then get the rock or the valuable thing to stick to the bubble and float to the surface. Think of a glass of beer. You've all seen a glass of beer? Put your hands up if you haven't. Good, everybody's seen a glass of beer. A glass of beer actually demonstrates flotation quite nicely. The beer is the pulp. On the side of the glass you get bubbles coalescing and floating to the surface. If you assume that there were particles in that beer, you wouldn't be drinking it, but those particles should be either hydrophobic or hydrophilic. The hydrophobic particles stick to the bubble, rise to the top, you have froth, you recover the froth. So that's, if Mum doesn't understand what flotation is, just show her that and explain it and she should get it. Simple. Well, it's not so simple. I live by two inescapable truths in my life. One is you need to grind to liberate the minerals from one another. If you don't liberate them, you're not going to make grade and you may not make recovery. Once you've got liberation, it's very, very important that you think about the surface chemistry of the things you're trying to separate. If you haven't got the right surface chemistry, you are not going to get a separation. So, liberation, hydrophobicity, they're the two words I'd hope that when you leave this room, they're imprinted on your brain. This is some data from a plant. It's copper recovery. And it moves around quite a bit. You've got recoveries down as low as about 74%, up to probably around 93%. Why? What's wrong? Why does it happen like this? There are a number of reasons why it happens like this. One is that maybe you haven't got liberation on that particular day. The reagents might not be right. The chemistry may not be right. Invariably, when we're running a plant, the things we actually measure and monitor and try to control, and we try to control the feed grade, but really we're at the mercy of the mining engineer as to what goes into the plant. Miners are usually paid based on tonnes drilled and blasted, or metres drilled and blasted, or tonnes up the shaft or out the pit. When miners don't get ore, they ship waste because their bonuses are based on tonnes. There's no mention in most contractors for mines about quality. It's all about tonnes. And this happened at Mount Isa when I worked up there. If they didn't actually mine real ore, they mined waste up the shaft, through the crusher, and in lead zinc we actually had a heavy media plant, so that would take care of their stuff-ups. So the feed grade varies, and it varies based on what the miners deliver. Some concentrators, Olympic Dam used to have a big stockpile, so they actually had a live stockpile that they could work on and they could get a reasonably consistent feed. Other mines, like Broken Hill, live hand to mouth. So what comes out of that pit or underground goes straight in the concentrator, and it varies dramatically. Particle size. We think we can measure it. Most plants measure it on a shift-by-shift basis. Some plants are lucky enough to have an instrument, but invariably the particle size varies because as the ore comes into the plant, it has varying hardness. So if you've got a SAG mill, for example, in your plant, if the ore is soft, the throughput goes up, the particle size is probably fine. Whereas if you've got very hard ore, the mill will fill up, you'll have to slow down your throughput, and you'll coarsen up the grind. So the particle size, we might measure it, but it's constantly varying. Throughput, that's one thing we can actually measure. And most operations try to run to a particular throughput which is developed from the annual budget. They need to get so many tonnes of copper or so many tonnes of lead, and that equates to so many tonnes on a mythical head grade that they've budgeted on. People do measure the pulp density, they measure reagent additions, some measure the pH, and where's Bill Skinner? Occasionally it is correct. They do adjust and monitor the airflow rate and the froth depth in the float cells. A lot of this is done automatically from the control room, and there's very few times that a control room operator will walk out into a plant to see what's going on. He'll rely on somebody out in the field to do some of these readings. But as we know, flotation is about the hydrophobicity of the surfaces of the particles we're trying to separate. There is no measure in there of hydrophobicity. There's no chemistry measured in a flotation plant which is relying on the modification of the surface chemistry in the process. So, what are the challenges? And this is my last slide, so hopefully we'll catch up on time. The challenges, as I see them, are to be able to measure liberation. Now, I'm not talking about grinding 100 million tonnes of ore to a P80 of 38 microns, because primary grinding is about liberating the non-sulphide gangue from the sulphides. Regrinding is about liberating the valuable sulphide from the gangue sulphides. So if you could measure liberation, particularly around regrind, you could actually monitor what you should grind to and reduce your energy consumption and be more specific on what you're trying to do in regrinding. A lot of PSI or particle size monitors, they measure a single point. It's either a P80 or a P50 or a P something. We very rarely look at the size distribution. If you could measure a distribution, that might actually tell us something useful, and we could use that distribution to try and operate the plant better. If we could measure the hydrophobicity, it would give us an idea of actually have we conditioned the particles we want to separate correctly so that they will attach to a bubble. Obviously, pulp chemistry, Bill's talked about the Magotteaux pulp. Measuring pulp chemistry is the first step in getting to some of that hydrophobicity numbers and trying to improve the flotation process. If we could measure residual reagents in the pulp, collector, frother, perhaps we can adjust those reagents so that we can reduce the amount we're adding and be more efficient. If we can measure all these things, it then means that we can actually improve the process control because we're actually starting to measure the critical parameters that drive flotation. So some of the work that's been done in the PRIF and in the training centre is heading down that way. The particle size monitor that was talked about just recently is very interesting. I'm quite interested to talk to you a bit more. Some of Linda's work with the MOF, some of who did the work with the collector, and I know Piotr is doing that. Again, that sort of stuff is really good, and needs the attention of the industry to be able to develop that to the point where we can actually put it into a plant and use it and commercialise it and ultimately improve the, I guess, the efficiency of the ore body, but by recovering not 85% of the copper, but heading towards 98% of the copper. Okay, I think I've waffled on enough. Questions, if you dare.
Any questions, Chris?
I've stunned them.
Everett's behind you.
You have a whole list of things. Were they listed in your order of importance? Or I should ask you, if you only had one thing you could have off of that list, which one would it be?
Well, I've got one already. I'm measuring the pulp chemistry live.
Okay.
That's a very good start. The pulp chemistry is actually a proxy for the changes in mineralogy. And with the trial that we've done up at Prominent Hill, it did show that by using the chemistry, we were able to control the collector, the air and the level simultaneously to get the better grade recovery position. We're trying to do an extended trial up there now. We've actually changed the way we think it should be operated, because in that Jamison cell, its key objective is to make a concentrate grade. So our algorithms now, you type in the grade, and then for the change in chemistry, it will then optimise the collector air and level on the Jamison cell to get that grade at the best recovery. Beyond that, if we can measure residual reagents, we can then start to cut down what you're adding and make better use of it. Liberation would be wonderful on a regrind, but I think that's a lot harder thing to do online. And it doesn't have to be every 5 minutes. If it was done every 3 or 4 hours, that would be nice. Then you could actually target. Today, or on this particular ore, we can regrind to 53 microns as opposed to sitting at 38 every day. Another thing is the mineralogy changes. If you're adding lime to depress pyrite, if the oxygen demand goes down, it tends to suggest you don't have as much pyrite coming to the float. You don't need to run at 10.5. Maybe you could reduce that down to 9.5. So rather than, because a lot of the depressants and lime are constant because we don't know how to change them, if we can actually measure something that's telling us a little bit about the mineralogy, we can actually make these things more dynamic, which should give us better metallurgy, better utilisation of reagents, lower carbon footprint and all the rest of it.
Thank you, Chris.
Thank you very much.
Dr. Piotr Pawliszak is a postdoctoral research fellow from the Future Industries Institute at the University of South Australia. Piotr recently joined PRIF to continue developing the moth sensors project. He is returning to academia from industry and completed his PhD in Minerals and Resources at the University of South Australia in 2021. His PhD research was focused on exploration of the hydrodynamic boundary conditions at various liquid-fluid interfaces and on the application of gained knowledge by designing, developing and testing a microfluidic-based sensor for the detection of the flotation frothers. And that is the work that Piotr will be presenting today. During his PhD, Piotr published 8 peer-reviewed papers in top journals, with one of his papers featured on the journal cover. His main research interests are microfluidics, novel sensing devices for mineral processing, the hydrodynamics of rising bubbles and bubble and droplet collisions with various surfaces. Outside of work, Piotr is very active and loves hiking, football, soccer, scuba diving and underwater photography. Welcome, Dr. Piotr Pawliszak.
Thank you so much for the introduction. So my name is Piotr, and sorry, can I use the pointer?
You can, but people online won't be able to see, so just keep that in mind.
Okay. So my name is Piotr, and today I would like to talk about the microfluidic sensor for the flotation floaters. And how do I use that? Okay, sorry about that. And okay, I'm going to talk about floaters. So obviously my project was related to the flotation process. And the main goal of my project was to develop the sensor that will allow for real-time measurement of the floater concentration. And the key achievement of our research was that we were able to design, fabricate, and develop this microfluidic device for inline measurement of floater concentration based on the bubble generation frequency. And the key advantages of these sensors are that it's quite cheap and simple because we just need high-speed camera to count bubbles. It's very sensitive, as even small amount of floaters will affect significantly the bubbles inside of the microfluidic channels. And it can be used for various surfactants having completely different adsorption properties. And why this is important? Because currently there are no methods available for inline measurement of flotation floaters. And to describe this problem, the flotation floaters are surfactants, the same as washing powder. And I think we can compare the flotation process to doing laundry because also bubbles involved. So, when we do this without this real-time sensor, it's like doing laundry blindfolded, which will lead to either overdosing or underdosing of washing powder, right? Which results in either too much froth or dirty clothes. And the same thing happens in the flotation because overdosing or underdosing of floater may have several issues, may cause several issues impacting either recovery or grade due to, for example, too stable froths or decreased probability of bubble attachment to the valuable particles. And so how we can measure the floater concentration? For that, we can use the interfacial tension because the floater adsorption at the interface results in interfacial tension reduction. And as floater concentration increases, the interfacial tension decreases. And for our investigations, we have selected two floaters which are commonly used, that is MIBC and Prof. So the first step of our investigations was to get interfacial tension values for our floaters, and we wanted to describe as well the adsorption properties by profile analysis tensiometry. And as we can see for MIBC, it's characterized by instantaneous adsorption as there is no interfacial tension drop over time, while the second floater, which is Prof, is characterized by slower adsorption kinetics because we can observe this gradual decrease in interfacial tension. However, the surface activity of Prof is much higher because lower concentrations were required to achieve similar interfacial tension drop. So we can clearly see that we are dealing with two floaters having completely different interfacial behavior, right? So then we were focused on the development of this sensor for real-time detection. And one of the technology platforms that has potential for deployment in industry to allow this dynamic inline measurement of surfactant concentration, it's microfluidics. So we fabricated a glass microfluidic device with coaxial geometry, which means basically that dispersed and continuous phase flow in the same direction. And here is our design of the microfluidic chip, where we have dispersed phase channel in the center where there is a air pump, And we have two side channels that meet this one channel where we introduce our continuous phase, which is actually the floater solution. And these channels merge together to form one main channel where we observe our bubbles. And within this geometry, the size of the bubble is only affected by the continuous phase flow rate and the interfacial tension. And why this is important? Because our analysis system was based on the high-speed camera observations of how many bubbles were passing through the channel over a certain time period. And the bubble formation frequency is directly dependent on the size of the generated bubbles. Okay, having this knowledge, let's have a look on the floaters effect on the bubbles inside of the microfluidic channels. So the presence of the floaters in the continuous phase results in the adsorption of the floaters at the interface, which decrease the interfacial tension forces that keep the bubble on the tip of the sparse phase channel. And as a result, smaller bubbles detaching at higher frequency were present in the microfluidic channels. And as we can see for both MIBC and Prof, for the same continuous flow rate, as we increase the concentration, the bubble generation frequency increased because the interfacial tension that is counteracting viscous drag decreased, right? And if we keep the floater concentration constant, but we increase the continuous phase flow rate, also the number of produced bubbles increased. So things are getting more interesting when we look at the interfacial tension and translate the bubble generation into the interfacial tension. And for both floaters, the bubble generation frequency increased linearly with decreasing interfacial tension, and the same dependency was observed for every tested continuous phase flow rate. And additionally, this sensing method based on the bubble generation frequency is very sensitive, as the drop of interfacial tension by 0.1 caused the increase in the bubble generation frequency of about 15%, which makes this method suitable for detection of even smallest amount of the floater molecules in the solution. And finally, we can normalize the bubble generation frequency with respect to water at given flow rate to receive this relative bubble generation frequency and plot that against the drop in interfacial tension. And after this scaling, the data of relative bubble generation frequency for both floaters, MIBC and Prof, and all different considered flow rates can be fitted into one straight line, showing that relative bubble generation frequency is independent of continuous phase flow rate, and it's only affected by the changes in interfacial tension, which means that this method can be used in different process environment, let's say where we use salt water or different process water, as we can always introduce this bubble formation frequency scaling by the value for process water. And additionally, despite the fact that these two floaters have completely different adsorption kinetics, the relative bubble generation frequency was the same for Prof and MIBC, showing that this chip can be used for various surfactants having completely different interfacial properties. And finally, I would like to acknowledge everyone who was involved in this project. So thank you for your support, Marta, Bill, David, Bron, and Chris. And thank you for your attention.
Do we have any questions?
This thing is complicated. Just to.
Everett's just behind you with the microphone.
I was wondering if you have enough understanding or models of the physics of bubble formation to be able to say on a theoretical basis that that bubble formation or the thing would depend only on the concentration as opposed to the flow rate.
Okay, so actually for this geometry, there is no available model that was established to describe that. There is something for similar geometry. That's why I made this assumption that it only, is dependent on that, but there is no clear model for this one, because there are a few different geometries in microfluidics. Like this is co-flowing, but we have flow focusing or T-junction, and they have slightly different models. So yeah, this is just something that has to be developed. That's with someone with more theoretical background, I guess.
Thanks.
Thank you. We'll now break for afternoon tea. We'll just have a quick 15 minutes. So we'll be back here just after 4. Please use that time to have a look at the posters of the PRIF work that are displayed in the hallway.